Yeah, it says you're recording.
Perfect. I'll pause that for a second. Okay, resume recording. Okay. Hello, everyone. Welcome to the IREC subteam overview meeting. So we're just going to be talking about all our subteams, what we do. You could draw similes to this to SL because a lot of the subteams are the same. But we have a lot different workload than they have, especially considering we kind of have a leg up on the competition since our competition was kind of canceled last year. So we already have a lot of design work done and everything, but we'll go more into that. So the competition overview of IREC is basically we're flying a rocket to 10,000 feet. In our specific rocket, we have two different payloads. So we have one payload that is active controls, deploying air brakes to slow us down in the air, to control our apogee, how high we go into the air. And then we also have Tyler's payload that he'll talk about soon. Is strict control. So when you have your parachute open, we can control where we land, which is useful in a lot of applications. And it's super cool when you think about it in like the frame of real life, because there's like SpaceX and stuff are trying to land their rocket in specific places. You need to get stuff to the ground at a specific place. It's a very useful thing. And when we're researching a lot about the payloads, we hear a lot about how the industry actually uses it. So yeah, aside from that, basically the competition is all about innovativeness. So our main goal is to try to make our design as wacky and as cool as possible, because that's how we get points in the competition. And also that's how we have the most fun. So a lot of, like I said, a lot of the design and construction work is already finished. Well, not a lot of the construction. We haven't done much of the construction, but some of the design is done, especially for my section, avionics and recovery, which I'll be going over shortly. But there is design that isn't done yet, such as Tyler's payload, and we'll talk more about that. And so for the differences between IREC and SL, I know in our GBM we didn't go too in depth about it, which is our mistake. So the difference between the two competitions are two completely separate competitions. So Student Launch works with NASA to go over, they do like design reviews and everything, and they build the rocket. They all have the same payload. They're all, well, they don't all have the same payload, but they all have the same, they're all supposed to do one thing. So I think this year it's something with a picture. So they all come up with designs to try to fit that singular goal. The differences between the competition is they have a lot more documentation. So they write documents to NASA. And our competition is more focused on designing. It's more focused on trying to innovate on design. So a lot of SL designs you'll see are kind of carbon copies of previous years, which is unfortunate, but that's just kind of how the competition goes.
Not bash on SL too much though. A lot of that documentation is like real stuff that actually matters though. So like it is good, like building skills. Don't
get me wrong. The documenting is actually a benefit for them because they learn a lot about how to do technical writing, and they have actual engineers review it. And then the legacy comparison between the two, basically both competitions have a lot of corporate sponsors. So you'll see a lot of like Raytheon people at the IREC competition. I personally know two different judges that are from Raytheon that are going to our competition. So that's super cool. A lot of industry people see it as a very cool thing. You don't know Raytheon is like the biggest producer of missiles in the world. So yeah, it's super cool. And yeah.
Also, if you guys have any questions, feel free to jump in on voice or throw it in the chat.
Yeah. So here's our leads. You can just talk to them on Slack. Yeah, if you want to, this is all recorded, so you can go back to this page and be like, oh yeah, I want to talk to Asia. This presentation looks super cool. Yeah, so here's my section.
Let's get her done.
Let's get her done. Basically, we just got to finish this, you know. Basically, avionics and recovery is the brain of the rocket. You see this brain over here? You see this rocket? That's us, okay? And this is like something that you'd see in industry. The other picture here, I don't know if you can really see my cursor or not, but yeah, this is something you'd see in industry. And it looks very similar to our avionics bay because they're very similar things, just a tube full of electronics. So yeah. First, I want to get into the most basic summary of rocketry because I know a lot of you guys probably entering this don't know a lot about rocketry, which is completely fine. There's a couple of events that happen on both SL and IREC rockets that I want to clarify. So we go up under propulsion, under the rocket's engine. Our velocity hits 0. Our fuselage separates, and a small parachute deploys. I'll post a visualization of this soon. And then when we drift to like 500 feet-ish, we have a bigger parachute deploy that'll make sure that we hit the ground at a slower speed than what we would with this small parachute. And then we drift to the ground. Basically, this is a visualization of it. You see we have this arrow, this blue arrow going up. So we launch, we get up to a certain apogee. Our rocket stops going up, and then the drogue parachute deploys, small parachute. And then you see the big parachute deploys, and that increases your air time. So, yeah. For IREC specifically, this is our rocket design we have right now. Basically, you can see how it's set up here. We have our avionics in the nose cone area. Avionics, again, is what controls all our events at apogee. So this is what controls when the drogue opens. It's what controls when we separate. And it's what controls when the main opens as well. And then we have this section here denoted by this yellow electric bolt. That is where our separation of our two body tubes happens. And basically there's a shock cord to connect the two sides. So they're still tethered together. And then in the middle of that is parachutes, but I'll show a visualization of that in a second. We have our drift controls slightly above our active controls. So the drift control will have all our electronics for the payload that Tyler will talk about, and active controls will have all their electronics for their subsystem. So yeah, if you remember that lightning bolt, this is what happens when it separates. We have our drogue coming out. We also have our main chute coming out. The main isn't unfurled until we get to 500 feet. And we control that through a an apogee dependent explosion. So yeah, basically, if you remember, the avionics is at the front. We direct separation and our main unfurling, and then active control or payloads will control the drogue, which is direct control. Yep. And if you were wondering why we do this small chute first and then big chute, it's because if we don't do it that way, we drift a lot. So if you have a main chute open at apogee, you'll drift very far. So like if you look at this line, that's what happened. The red line is what happens if you deploy at apogee. You have a lot longer air time, which means you have a lot longer to be pushed by wind, which means a lot more drift, basically. Bigger chute equals slower fall. It's more time to drift, which is something that hopefully Tyler will solve with this amazing payload. And there's a lot of factors to consider for us. Which is better, the drift control on the main or the drogue? We decided drogue, but who knows? It could be up in the air. It's a control. I'm sure Tyler gets into it. Yeah. So, and then we have the question: if drift control works, do we even have to worry about having two big parachutes? Because, like, hey, if it works, then we won't be drifting. Another thing to consider. Maybe it's a fun question. And then basically our big overarching question is how we work with Tyler to get our avionics integrated with his drift control. So back to avionics, that was kind of more of an overview of the rocket itself. This is what we are doing in avionics right now. Basically, we have this tube, if you see on the side there. Sorry, my zoom bar is like blocking it. But yeah, we have this section here. We have batteries being held on the top. The wires from those batteries go down this middle sled area to our altimeters. The altimeters, they basically eat air pressure and say, tasty. I think that I'm at so-and-so feet. And then once they say that, oh, they can also kind of tell velocity a little bit. because they could tell if the rocket stops moving, because they're like, oh, it doesn't feel like I'm getting any higher anymore. So that's what controllers are main separation at Drogue. So yeah, and there's switches to turn those on and everything, and we all have to put together our designs to try to basically build a bay that works. And then we're also thinking of a camera idea. This is kind of an obsession of mine. I don't know if it'll ever happen, but one day I do want to get this camera to work, hopefully. And yeah, we also have this, which is basically our ejection charges, our little explosions that do the separation that I was talking about. So you basically need to route it through terminal, do all that. There's that eye bolt there. Basically, you want to make sure that the shock cord delivers from opening and pulling on the other side of the rocket won't break it out. So we need to do testing with that, and I'll get more into that in a second. Yeah, so work we still need to do. We completed a lot of the design work already, so that's really good, especially if you're like a freshman and you don't know a lot about design. You can look at our design and be like, oh yes, this looks cool. And then you could also help us with design, because some things are poorly designed that I'd like to have redesigned this year. And if I have someone to help me do that, that'd be super cool. So yeah, basically we're gonna be printing prototypes of our sled to make sure it fits in the tube, because there's a lot of tolerancing stuff that goes on with shafts and holes. And there's a lot of issues that comes with the imprecision of 3D printing, which the big sled thing that has all our wires in it, that's 3D printed. So yeah, kind of annoying. But coming up with an external camera idea, all that will be done by October. Hopefully we'll have everything constructed and built by November, maybe early December. But most of our time, I think, is going to be dedicating ourselves to helping active controls and payload, because they have the biggest amount of design work ahead and they have the biggest amount of construction ahead, since we already kind of have a head start on our end. And we're always going to be double checking our design, because I'll be honest, I feel like it could have some improvements that would make it better. And it's good to review your designs, especially with new faces in here. A lot of people have good ideas about things, and a lot of people are able to spot mistakes that you don't initially see. So I'd love to go over my design more in depth sometime. Yeah. So this is your time for questions for active control, or for avionics and recovery specifically, before we switch over to payloads. Anyone? No, no. Okay, Tyler, you want to go?
Yeah, I can do active controls first, I guess.
Yeah, sure. Pause share, I guess.
Yeah, if you stop sharing, then I will.
Does it let you share right now?
Guess so.
Okay, great.
Okay, so active controls has been being developed over the past couple years. A lot of these competitions revolve around hitting a certain altitude. So the idea in active controls is to be able to control our drag as we approach apogee, so that we can, perfectly hit that number, because a lot of competitions score you on that basis. These are Asia's slides, so if you want to know more, you'll probably have to talk to her. But yeah, so manufacturing is the big thing, I guess, for them this year. Last year we 3D printed some stuff. It was more of a prototype than a finished design. We want to do everything out of aluminum this year, so it'll be a lot more structurally sound. The parts we 3D printed had a lot of issues. Some of the edges were not very good, and pressure kind of prevented them from swinging out fully. And then the code is going to be another big thing, because we can constantly be improving that. There's a lot of variables that we'll have to deal with as we go up, between like the motor not, having the perfect amount of impulse that it says, or wind kicking in, stuff like that. There's dozens of variables that we'll have to account for, so we can constantly be making that better. Here's kind of the physical design of it. On the left there, you see kind of those triangular fins. On the other side of that that's hidden under there, there's another similar shape, but it's geared. So basically what happens is once the motor burns out and we're just kind of coasting, at some point, the motor that you can see down on the bottom right there will spin the gear in the middle. It'll spin out those fins, and then that'll induce drag. And if we do the code right and time it right, it'll stop us at the perfect point. Yeah, so those are all the things that Asia needs. Yeah, she couldn't be here today, but if you're interested in joining that, yeah, we still have a lot of work to do to perfect that, so hit her up, I guess. Any questions on active controls? No, okay. I'll go ahead and do drift control then. All right. There we go. All right, so this is a video from our launch last year and was half the inspiration for this. Whoa. Sorry, we'll watch the fun part again. And this will kind of help show the recovery system too. There's the Drogue chute. And there's the bigger main as it's almost to the ground. And that's the whistle to say it's about to land on your head. Pay attention. So yeah, that was a feet thick of mud that landed in, and water got all up in the active control bay we were trying to test, and that sucks. We've had other ones that land in trees. Yeah. Oh yeah, sad face. Very true. We did save all the data though, it didn't kill it. But even just, yeah, if it lands in a tree, I've seen a group that landed like 100 feet up in a tree off the side of a road. You know, how are you ever gonna get that? So generally just trying to prevent that kind of stuff. Next slide, please. Thank you. Okay, so yeah, we've already talked about the goal a couple times now. Do you have any onboard cam footage? Somewhere I do. Probably not this computer though. Anyway, yeah, so we talked about the goals, yeah, and eventually we want to integrate this into avionics and be able to use it on basically all of our rockets. That way we don't have these problems in the future. So the first thing to look at is the parachute design. This is a traditional one, pretty straightforward. Just pops out of the airframe, very easy to deploy. All the shroud lines at the same length go to one point. But the downside of it is that that simplicity also means you have no control other than how fast you fall, which would kind of defeat the entire point. So we need something controllable. There's a couple of things we looked at. The first was a parafoil, which difficult to deploy, and you see all of those cells across the whole thing makes it very structurally complex. So if any of the shroud lines tangle, and the shroud lines are the white lines coming off the sides there, if any of those tangle at all, it'll completely destroy the structure of it, make it completely unstable, and then we will fall very fast. These are also like super controllable to the point where we might actually be moving around too fast. So that's where we kind of went with a middle ground, which is the Rogallo Parawing, which, fun fact, they considered using they're considered in the Gemini program to land astronauts. Yeah, it's kind of a middle ground because it's less controllable, so it won't turn quite as fast. And then it's a little simpler than the parafoil. So this is what we're going with for now, but still we're in a very much a prototype phase, so this could change in the future. Any questions before I go on? No, okay. So for our sensors, we have the GPS is the biggest one. That's going to tell us our position and our altitude. I'm also thinking we'll probably want an IMU, which is an inertial measurement unit. That will tell us more how the rocket is actually moving. We can get like pitch, yaw, and roll from that. And that may update a lot faster than the GPS. Yeah, some GPSs are only like update like once a second, which is not super good if you're turning at any significant speed. And then also the accuracy of them may not be great, so we might want a little more input there. We'll send that data to a microcontroller, which will run the code we give it and then tell the motor where to turn. Yeah, so physically, there's the motor on the wheel, and then we'll have the lines come down through those two holes in the top bulkhead. Those will go around that wheel, and that'll be what actually turns the parachute. And then we'll stick this on a more traditional sled design. I'm thinking about putting like these ribs through the middle. That way we have extra room, because I don't think everything will fit on just the sled, because we have a battery, a GPS, IMU, maybe an SD card too, depending on what microcontroller we use, because we're going to want the data off of this. Yeah, so we have decided to do this with the Drogue chute, which is the little one that deploys first. And even though the main chute is larger and will give us more control, the Drogue chute deploys for much longer, and we cover much more altitude with it. So we can actually cover a lot more distance, even though we have less control. The other nice part about doing it under Drogue is that you can see on the bottom of this graph here, that's the time it takes. So this peak up top of the red line is where Drogue deploys, and where you see this green spike in the slope decrease on the red line down there, that's where main is. So we have way longer when Drogue is out. So if we do have problems deploying, or it's a little slow or whatever, we have time to adjust. And then the other nice thing is that, if this experimental payload happens to fail, we'll still have a traditional main chute, so we won't just plummet into the ground and destroy everything, because that's bad and dangerous. Okay, so then last thing I have is just a few things that I'm thinking could be difficult. Finding when exactly we hit apogee without an altimeter, that could potentially be an issue, but I think GPS should give good enough altitude data, that'll be fine, but we'll have to look at that. Tangling is one of the biggest ones. We're gonna have a shock cord going from the top of my bay up to active controls in the nose cone, and then around that will be more shroud lines for the actual parachute. And if any of those three lines tangle, that will completely destroy the stability of the parachute, and that would be a big problem. So keeping those separate is going to be one of our biggest challenges, I think. The other part is we're going to have a lot of weight on that wheel that's supposed to steer. We want to make sure that that doesn't keep it from actually steering. Keep it off of the motor axle so that it doesn't mess up the motor. Power, we have to be able to power the motor, and it has to last long enough, so we'll have to be very careful with that. And then I talked about it a little bit already with the GPS data not being updated very quickly, so we'll have to manage that input delay. So that could be annoying if we're turning faster than we're getting data. Went through a lot there. That was all I had, though, if anyone has questions.
Yeah, I have a question.
Yeah, go for it.
The new design for the parachute that's not the parafoil, how is that different from a parafoil? Like, what makes it different?
So the parafoil is a bunch of cells. Like, go back to it. Yeah, like you see, like these rectangular cells. That's what makes up the parafoil. The parawing, the Rogallo design, is two conical sections.
Gotcha. Okay.
Yeah, so it's simpler that way. That is what we tried to build last year, but yeah, the shroud lines weren't quite right. But that's what I'm thinking, actually, for a prototype going forward, we might try a rigid design. That way that'll be easier, and then go from there, at least to test the concept.
You said that you were going to try to use the GPS for altitude rather than an altimeter. Is that because you're trying to save as much space as possible, or battery, or what's your goal there?
Yeah, all of the above, because we'll be The only thing that will have an altimeter will be Bryce's section. So I would rather not have to put in a sensor that something else already covers. Yeah, like you said, more battery, more space, more cost. If we can avoid it, I would like to do that.
All right, cool.
Yep, good question.
So you guys are getting all of your movement data from a GPS in the rocket, but if the rocket is swinging about and rotating as they usually do, how are you going to get accurate data from that?
That's partially why I went to IMU, because yeah, the GPS might not be super accurate. That'll be more of like a long-term, are we going generally the right direction? Yeah, to make sure we're not swinging around wildly. That's why I went to IMU. All right, nothing else then. I guess that's back to you, Bryce.
Yeah, sure.
Okay.
So we just have a couple of slides for the other people who will be presenting. Hold on. Hold on. Yeah, so just on active controls, there's like a lot of talk about with like how to code it. We were talking earlier about integrals of using integrals to find the distance you need to deploy the active controls, or using matrix that holds like all the information regarding it. But yeah, I don't know if you guys caught that first little bit of discussion we were talking about, but it's a big problem. If anyone knows anything about coding, they're definitely the people to talk to, active controls. For structures, we don't have a lead yet, but Adam told us, and Adam is our project lead, he told us that he's about to pick one. So yeah, their work consists of like constructing all the composites. They work with like the basic structure of the rocket, like holding the motor mounts, the fins, a lot of the composite materials like carbon fiber, they make that. Yeah, and they also do a lot of testing regarding the rocket, making sure the composites they make actually work, making sure that the motor mount is nice and sturdy, and they do a lot of the manufacturing work. So, and then flight dynamics, Bilal is here if you want to talk about that.
Hey, okay, so yeah, I believe we have a motor selected already, the M2500, which, yeah, pretty much like that might be subject to change, but I think we already ordered it, so we're good on that. From now on, the overall, if I can show you the dot or the open rocket file, for the most part, the design is already finished. We're mainly going to be this year like helping active controls determine like certain numbers they need to accurately predict where the rocket's going to be. We're also going to be performing CFD analysis, see if like the rocket can handle the forces of the flight. So like for example, on the on active controls, can the fin actually withstand deploying and taking that wind force at a given velocity, for example? And then we'll run that in ANSYS or SolidWorks Flow Sim, depending on which one we get. But yeah, a lot of things is up in the air right now because I'm like a new lead. So right now, what I've been doing is just joining other sub teams. You might see me at SL Flight Dynamics just helping out, or you'll see me in like other IREC teams just watching and seeing what they need our help for. Because right now, a lot of the stuff is done, but we still have a role in the team to like help them figure out stuff. Another thing I was looking at doing was seeing what are the compressibility effects when we go over Mach 0.3 and 0.8, because right now when the max velocity of the rocket is Mach 0.8, so we would like to like accurately simulate that. Yeah, so hit up my Slack, hit up my Subteam. That's all I got.
Yeah, so this is like super helpful if you're like an aerodynamics person. If you're an aerodynamics person or an aerospace engineer, because CFD is something that you would be doing a lot in your job, post-matriculation.
CFD is computational fluid dynamics.
Yeah. So basically, you're like seeing what happens when air hits you. And you use that to calculate a lot of stuff, and it'll be super helpful when it comes to active controls, because we basically need to know how much air is hitting our rocket and how much that slows our rocket down by, so that active controls could translate that into code and translate that into software that like slows us down before we reach, where we want to go. But yeah. And then just, I added some final slides just in case you were still a little bit fishy about how the rocket flight works. But now that you know all of the subsystems, it should be easier to understand. So we start at launch, the first star. We go up by the second star, our motor will be out of propellant and we'll just be drifting up with residual energy. Somewhere in that time, active controls will open up and preferably get us to 10,000 feet. And then somewhere in that time, active controls will retract because we don't want it damaged. We'll hit the ground. Our drogue will open, of course, and we'll drift down. If Tyler decides to keep it with with his drift controls in the drogue, he will be controlling it so that it stays around our launch site, or pushing it to a specific place he wants to land it at. And then for the last part, of course, we have to open up our main, which is one of our objectives at avionics and recovery, because we have a special little device to do it. And we gotta learn how that thing works. So yeah, here's just an overview. Basically, yeah, that's what I just went over. But yeah, so just a quick FAQ, last little bit. How much experience do you need? Nearly none at all. A lot of us started as freshmen, and yeah, you don't need a super lot of experience. Supportive rocketry is very open. So yeah. Which sub team do I join? As Bilal said, join as many as you can. Dedicate yourself to your favorite. We all work very closely with each other, especially this year, since a lot of our design work and construction will be focused around the two payloads we have. So yeah. And then if you have any questions about where you learn more, of course, we are always open. I love answering questions. And our meetings will help, obviously, hopefully. There's also YouTube. NASA posts articles about high power rocketry that are a fun read. If you're confused about topic, just look up NASA high power rocketry on Google or something. There's Yield Rocketry Forum, there's r/rocketry. There's a lot of avenues to learn more with the amazing sport model rocketry. And yeah, so if there's any other questions.
Even if it's super general, if you're new to rocketry, that was probably a lot, but
yeah.
using something other.
To answer Willard's question, we're probably going to be using ANSYS. With SolidWorks, we're probably going to use FlowSim, like the FlowSim package, mainly doing like computational fluid dynamics this year. We might touch MATLAB, but most of our work is still going to remain in OpenRocket, obviously, with some CFD on the side.
And I'll be touching on a different language other than MATLAB, but not that different conceptually. Whatever I need for the microcontroller we picked.
Yeah, no writing the rocket, unfortunately. There's maybe.
Is drift control autonomous? Yes,
yeah.
That is the goal.
You're actually like not allowed to control things like do like
Yeah.
RC or anything, because then the people who preside over us, the National Association of Rocketry, will be like, okay, that's a missile if you ever control it. So yeah, it has to be all autonomous.
How are you guys setting your like landing target for the drift payload?
So the GPS will just use whatever coordinates that it gets when we start it up, which will be the launch site.
Ooh, side note that I wanted to note in my presentation. I'm going to try to get, so to have that GPS, we need people who are FCC ham certified. So if you want to join my team, I'll tell you the ropes of basically how it works. So we could get a second person who's also ham certified, so we can make sure that if I'm sick or something, we could still fly the rocket.
I didn't know you were ham certified. That's good.
Yeah, baby, let's go. If that's all the questions, our Slacks are always open. For future meetings, I'm going to try to do joint meetings or like really close to the same time as Tyler, especially considering like most of my design work is done. So it'll kind of just be update meetings based on the construction we do. And probably a little bit of design as well, because I still want to go over it with all the new members, make sure everyone's up to date on it. So yeah, I'm probably going to be doing joint meetings with payloads and Chop.
Yeah, Solar Park is closed. We don't have any ability to manufacture right now, technically. I think, actually, what's today? I think they're supposed to meet on that yesterday, actually.
Yeah, on September 14th, they went over a thing with all the design team people about a reopening plan. And basically, you just need to submit some paperwork, I think. And labs should open up pretty soon. I suspect that by, what's the next month? September, October.
October.
Yeah, October, we should be able to start manufacturing for sure.
Yeah, it'll probably be very limited, obviously, like social distancing and masks, and it'll be a pain, but at least we'll be able to do it.
You have any extra questions? Slack is always open. I'm pretty sure that in a few minutes, or maybe he'll do it right after this presentation, Bilal is going to have a meeting about certifications. And in that meeting, you could probably learn more about how basic model rocketry works if you were confused by my amazingly put together slides. And he's also going to talk about how to get certification in rocketry, which is a cool experience to have to build your own rocket. And also it's like the thing you throw on your resume, haha, I'm rocket certified. But yeah, it's super cool.
How many people are brand new? Just throw up an emoji or something, just so you get an idea.
Dot.
All right, cool. Got new people.
Hey.
Yes, I know, like, for a lot of people, a lot of this probably just went, like, over your head a lot. You didn't know what to ask. I know I felt like that a lot, but just, like, stick around, keep going to stuff, and, like, we'll teach as we go. And really just jumping in with both feet is how you'll get more involved. That's what I did a couple years ago to become a lead in the first place. Just, hey, what can I do? I know how to do this thing. All right, cool. I'll pick that up.
Yeah, and I should be uploading a thing of the recording of this soon. So if anything you missed in the meeting, you could just go back on that and look at it. But
Yeah.
Can I have a copy of this recording if you want to put it up on the YouTube?
of course, Joel.
Okay.
Thank you. Cool.
Well, are you running the certs meeting?
Yeah, do you want to get started with the search meeting?
Well, I mean, I I had like the Zoom already up for it, so we have 20.
Okay.
Yeah, so
If you guys want to head to that, you could go into there. I'm not sure if he's going to start till 6 because he didn't.
yeah.
Probably doesn't want to confuse everyone. Yeah. Okay. Well, thanks for coming, everyone. I guess. All right. Bye.
Bye.
Bye, guys.